So today I'd like to present our results of leaching lead from aluminum pots and pans, which was done from 25 different countries. The results are summarized in a journal article, which is actually coming out in July 2025, coming to a newsstand near all of you, I am sure. It's also available online, luckily. The genesis for the leaching study that we did came from Pure Earth's rapid market study, where we collected over 5,000 products in 25 lower and middle income countries, everything from cosmetics to toys to aluminum cookware, et cetera, et cetera. Included in those 5,000 items were over 500 metallic cookware items. And that's what we're going to be talking about today, and specifically the leaching of lead from some of those items. In terms of the over 500 cookware items, which again included things like plates, spoons, and pots and pans, we found some alarming levels of total lead in these cookware samples. I think we had a high of 10% lead in some of the samples. But again, these were plates, spoons, pots, and pans. And today, we're going to focus on aluminum pots and pans and not on the other cookware items. And so you may ask yourself, where does the lead come from in aluminum in the first place? Why are we concerned about it leaching into our food? And this work was from Wiedenhammer and Perry Gottesfield, who's here today, some 10, 12 years ago, who found that the feedstock for these aluminum cookware are things not like just Diet Coke cans, which would be nice, but aluminum engine blocks, radiators that are potentially soldered together with lead solder, cans with lead solder, and also used aluminum cookware. In addition to that, electronics. So everything goes into a big pot, and if it melts, it can be formed into aluminum pot or pan, specifically in lower and middle income countries. What do these pots and pans look like? This is just a brief example of pots from Indonesia, Bangladesh, and Ghana, just to put things in context. We tested all of the cookware items. It was actually 115 for the total study. And again, we found pretty high levels of total lead in the cookware samples. I think the highest was 16,000 in the pots and pans, and over 75% were above 100 parts per million, which you'll hear is a reference level we used in this study. Only 4 of them were above 10,000 parts per million. So total lead, big deal or no big deal? Hard to tell. It's a hazard versus risk question. And will it leach into your food is the bottom line question we tried to answer. In order to do that, you can't test for total lead with an XRF. You actually need to take the pots and pans and subject them to some leaching, which is what we did. So how you leach them is definitely a very important question, and what you get into the leachate, or ultimately your food, is a function of many different things. And we considered some of these factors in the early part of the study and came up with a standard leaching procedure for 100 pots and pans. So we'll get to that. So one of the questions we addressed, heated versus unheated. We heated, first we put 5% acetic acid in pots and let them sit there for not hours, but days. And then we also took a selected number of the pots and subjected them to heated leaching, where we boiled them for several hours, and again, measured lead concentrations in a time-stamped series throughout. And what we found was the heated leachate was 2 to 3 orders of magnitude higher than unheated room temperature leaching, even if it was left for days. And these are very high levels, of course, 10 being the drinking water standard, and finding levels of 200 to 20,000 is significantly above that. Replicability we also looked at, like can you take the same pot and leach it repeatedly and get the same results? It's an important research question and an interpretation question as well. And we found out that no, you can't. You leach the same pot over and over again. We did 7 pots 6 times. We found that the lead levels were quite variable as we went, generally decreasing. Sometimes they went up and sometimes they went down. Meanwhile, the aluminum concentrations, also extremely high, were way more consistent. over time. And we'll get back to this later. We also found that old pots tended to leach old pots leach less lead proportionally than the new pots. We'll also get back to that. The addition of salt, common in cooking, we found that there was a marginal increase in leachable aluminum, but not an increase in leachable lead. It was a marginal decrease. So what we settled on was basically taking our 100 pots, filling them 80% with 4% acetic acid, boiling them for 2 hours, and testing the leachate for total lead and aluminum. Okay, and what do we find? This is the summation of all 100 pots with total lead on the X, and on the Y-axis we have leachable lead. And there's a correlation, right? The higher total lead, we see generally higher leachable lead. But there's a lot of scatter here. And keeping in mind this is also a log-log plot, it looks worse if it's not, okay? And you can see the R value, the correlation coefficient of less than 0.3, which is embarrassing, right? Now, would you expect anything better? I'll tell you no. But just to put things in perspective, for a pot with a total lead of 1,000, you could get anything from leachable lead from a few parts per million to a few hundred parts per million. That's not a great correlation, right? And we'll talk more about why. I want to draw your attention to this part of the graph, which indicates that of the 20 pots that had less than 100 parts per million total lead, we only found one that leached above a drinking water standard. So in terms of a threshold, that's where we come up with our 100 part per million value of total lead being a good threshold for what could be a significant source of lead. So getting back to the scatter and my correlation coefficient. First, the total lead that you're measuring is with an XRF. Generally, obviously, we tried to do it on the interior of the pot, but sometimes the pots were too small. We had to do the exterior where liquids are not in contact with. Some of the pots were very variable and heterogeneous in our XRF measurements, and we took a median value. So how well that represents is another question. And then, as you saw in the pictures, our 100 pots, they were all sizes and shapes, okay? And they ranged, I think there was a median of like 1.6 liters, but they were quite a range. And that, of course, alters the surface area to volume ratio in each pot. We didn't try to segregate that. And then also, you know, these are supposed to be uncoated, untreated pots that we collected. Of course, we don't know the actual manufacturing techniques for all of the pots. What we did separate for, which I'll show you shortly, is cast versus wrought pots. Cast pots being molten aluminum poured in a mold and allowed to cool slowly. Very common manufacturing technique. And the other method is a wrought pot. It's a mechanical way. You push form the aluminum into a sheet, you form it into a pot mechanically at cold temperatures, and that's a wrought pot. Now, if you separate the wrought pots and the cast pots, you start to see some dramatic differences, right? The wrought pots tend to leach less lead than the cast pots, which is an important finding. And you can see my correlation coefficient at least went up to something a little higher, which was nice. Okay, so there's this story here. Why? So we looked at some of these pots, the cross-section, using SEM and EDS, and we looked at cross-sections of the pots. And you can see the upper one is a cast pot, and the two lower ones are wrought pots, okay, from rolled aluminum. And first I'll show you the two bottom ones. The rolled aluminum has an actual structure. And you can see the light gray is the aluminum, and the dark gray is either lead or other like iron-bearing silicates, et cetera, other inclusions in it. And you can see that the wrought pots have an actual layering to them. And the cast pot is very different. Cast pot, you know, the aluminum will crystallize first, and the lead will then crystallize later at a much lower temperature around the aluminum grain boundaries. Okay, and then you have the you have the acetic acid attacking the aluminum. And again, these are cross sections, and they're forming in very different patterns. And so the cast versus wrought, you know, I think that this, particularly with the wrought, the layered nature of it does impact the amount of lead that can leach out at any given time. And as the aluminum dissolves, it does it in preferential pathways. Okay, the one on the bottom is an old pot where you can see that it's actually quite deep into the pot, and it does, again, follow preferential pathways. So there is a question of the accessibility of the lead to the leaching solution as the pots wear. Again, another close-up. This shows the lead inclusions at a much finer grain, also in a wrought pot. So what does all this mean in terms of blood lead levels, which we've talked a lot about? Okay, and we used, similarly to my colleagues yesterday, the EPA's AALM to model blood lead levels based on our leaching concentrations. Okay, and this is what this looks like. And it looks sort of like the graphs yesterday with one key difference. The greater effects were on older adults, okay, women of childbearing age, and the lesser impacts were to children. Okay, and children are definitely in the model and in real time, not just in the model, actually. The children absorb greater amounts of lead. But what we adjusted for was a dietary intake, that the children eat much less. Okay, and so that's why we see a much greater effect in the women of childbearing age. So there's a lot of limitations in what we did, especially with respect to the modeling. We're modeling this based on acetic acid, which is acidic. It's supposed to represent a tomato sauce. What it doesn't represent is rice cooked in the pot, cassava, other staple goods that forms the predominant diet of most people. So leaching with acetic acid, boiling it, is great to certify a pot is safe under most conditions, but it's probably very poor at estimating what actual exposure is based on actual dietary consumption. In summary, heating was really important to leaching, 2 to 3 orders of magnitude higher. This says 1 to 2, but that's a mistake. You know, our 100 part per million level for a significant contributor to leachable lead in the leachate, I think, is a good one. And generally, yes, higher pots with higher lead, total lead, tend to leach more. Gas pots leach more than the wrought pots, and new pots leach more than the old pots. Our replicate leaching was poor, but that's okay. And we also had poor correlation between how much aluminum versus how much lead leached. More leaching aluminum did not necessarily result in higher lead. Okay, and I think our SEM EDS work helped shed some light on the mechanical aspects of what's controlling the leaching and the environmental accessibility of lead. And our blood lead level monitoring is good. It is actually consistent with some of the work that Katie Fellows did, who's here today, which showed similar blood lead levels for Afghan refugees in Washington State. So, and again, finally, the boiled acetic acid is great for certifying cookware as safe, but maybe poor for or overly aggressive with respect to actual exposure. And just to acknowledge all of my help that I had, I didn't collect or bring all these pots to me. And thanks to Lexon Geen, who's here, who helped with some of the early studies at Columbia, James Brown, certainly Open Philanthropy, who helped fund this, who's here also. So thank you very much.